So today we're talking about our parallelograms. We're back on our hierarchy. We're going to fill that out. And it's a nice, easy day because it's just one shape. Last time we did 4 different shapes on here. Today, only parallelograms, right? So it's going to be way less information. Let's start with the definition. What is the definition of a parallelogram? Two pairs, parallel sides. So you can pause the video if you need to write this down. Symmetry line-wise, let's see. Do you feel that, like right here, this would be a symmetry line of the parallelogram? Is everything on the left side exactly the same as everything on the right side? Probably not, you know. And if I went like this away, do you feel that that is a symmetry line? Any of those symmetry lines? Nope. The fact of the matter is that a parallelogram does not have any symmetry lines. There is none. When it comes to the diagonals, we want to know if there's anything fancy about it. Remember, like the fancy things could be, they could be perpendicular to each other, they could bisect each other, and they could be equal. Those are the 3 fancy things, and one of those does happen. The diagonals of a parallelogram do bisect each other. They bisect each other. And remember, that means that they cut each other into 2 equal pieces. They bisect each other. So when you write this on your test, just by putting the word bisect isn't good enough. You have to say bisect each other. Here's what that's all about here. So on my little drawing here, I got a blue diagonal and I got a green diagonal. You see how the blue one totally cut the green one into 2 equal pieces. Thank you, tick marks. You see those, right? And then the green one totally cut the blue one into 2 equal pieces. Hey, talk with your neighbor real quick. Are the blue one and the green one the same length? Talk with your neighbor. Those are not the same length because we would have said equal here. All these guys do is bisect each other. So let's pretend the entire blue thing is 12 units long. Then would you believe this is 6 and 6? Are you with me on that? If that whole thing is 12 units. And what if the green one was 10 units long? Then wouldn't each one of these be 5 and 5? Do you see how they cut each other into 2 equal pieces? It's kind of weird. And then there's 3 properties of a parallelogram that we're going to have to remember. The cool thing is you know a lot of them already. Like, let me just give you this. If this side is 10, does anybody know how long this side of a parallelogram is supposed to be? 10. And if this side was 4, then shouldn't this side be 4? That is the fact that opposite sides are equal in a parallelogram. That is one property of parallelograms that I think we knew in the first place, that opposite sides have to be equal. Opposite sides have to be equal. Another thing is that opposite angles are equal in a parallelogram. Opposite angles are equal. So like if I numbered these angles 1, 2, 3, and 4, you know, opposite angles are like 1 and 3. You see that they're like a cross from each other. They're not consecutive with each other. So if this one is 100 degrees, y'all, then guess how much that one has to be? 100 degrees. The opposite angles have to be equal in that case, right? And then the third property is that any 2 consecutive angles are supplementary. Any 2 consecutive angles are supplementary. So back to my picture, if I had these 1, 2, 3, 4, again, any 2 consecutive angles, would you believe 1 and 2 are consecutive angles, right? They're right in a row. 2 and 3 are consecutive angles. 3 and 4 are consecutive angles. 4 and 1. I'm just going to put 100 degrees in here again. What should the measure of angle 2 be, since any 2 consecutive angles have to be supplementary? What should this one be? 80 degrees. And then how about this? These are consecutive angles, right? If this one's 80, how much has that one got to be? 100 degrees. Well, look at that. Boom. Aren't those supposed to be the same anyway, right? You know. And then how much has this one got to be? 80 degrees, so boom, you know, those opposite angles are equal. Any 2 consecutive angles are supplementary. Do you see how parallelogram is connected to trapezoid? Like right above it up here, there is a trapezoid. Isn't the property under trapezoid that consecutive angles between parallel sides are supplementary? Check this out, dude. Are those sides parallel to each other in pink, yes or no? Yep. Are those 2 sides parallel to each other in green? If you go around the clock, you're always going to be between parallel lines, right? So that's why any 2 consecutive angles are supplementary. Cool. That's pretty much it for our hierarchy. You want to keep it out so we can use it, you know, but let's go to the practice sheet. Here it is, dude. I want to tell you a secret. If you can get this down, you will know the bottom. because everything underneath here totally flows. And I'm going to just kind of do it now. I'm going to just work on like the diagonals. I'm going to show you something. Why don't we do this on our hierarchy? You're going to save your life. What is true about the diagonals of a kite, guys? What is true? They are, why don't you please put a big P right here. Those diagonals are perpendicular. Let's go to parallelogram. What is true about the diagonals of a parallelogram? They bisect each other. And over here on isosceles trapezoid, what is true about the diagonals of an isosceles trapezoid? They are equal. PBE. You guys have known me long enough. I make up dumb little acronyms, weird little phrases for things. PBE. I made this up years ago. You can make up any phrase that you want, but I call it peanut butter every day, right? PBE. Peanut butter every day. If you're allergic to peanuts, I'm sorry, you know, but it's like peanut butter every day is what I do. How does that help me? I can now go do all of the diagonals real quick because question, do these like marry together? Would you believe that the rhombus's parents is the kite and the parallelogram? Like one of them's mommy, one of them's daddy kind of thing. Those are the parents. So guess what's true about the diagonals of these guys? Do you think it should be perpendicular? Does one of its parents have that property? What do you think, yes or no? Yep, so these are definitely perpendicular. Do you think that they bisect each other? What do you think, yes or no? Yes. The question is, do you think that they're equal? Did any of the parents have any of that going on? That didn't work. So check it out. Let's go over to rectangle. Should a rectangle's diagonals bisect each other? What do you think? Is that one of the parents? Who are the rectangle's parents? Let's just kind of talk that out. The parallelogram and the isosceles trapezoid. So what do you think? Should this guy's diagonals bisect each other? Is that one of the parents' properties in that case? Should they be equal? What do you think? Totally happening. And then finally, finally, when it comes to the square, could you tell me who the square's parents are? Who is the square's parents? The rhombus and the, and a lot of people get that because it's like, oh yeah, the rhombus has 4 equal sides and the rectangle has 4 right angles. If you put them together, shouldn't you get a square out of that in that case? So would you believe that the square's diagonals are perpendicular because one of its parents has that going on, right? It's got some perpendicular. What do you think? Should they bisect each other? Should the diagonals of the square bisect each other? Yeah, both of its parents have that going on, so it's like, that's cool, it's going to bisect each other. And what do you think? Should the diagonals be equal? Do any of the parents of that square have that going on? This is how a hierarchy works, dude. If you know the top of the hierarchy, the bottom is going to flow. I guarantee you, you know its definitions already, right? You'd be cool with the fact that you know those definitions. You just figured out the symmetry lines. We'll talk more about it next week. But all you've got to realize is where the symmetry lines are, and we'll talk about them in class. But if you can memorize the top half of this hierarchy, the bottom fills itself in if you get how it flows down. Are you kind of okay with that? So it's just going to get, what I feel, easier and easier and easier because everything is the same story all over again. So, all right, now that we know our properties of our parallelogram, let's use them because they say the shapes here below are all parallelograms. Find the missing values using algebra. You really got to ask yourself this: what do I have expressions on? Do I have them on sides, angles, or diagonals? And you can tell that these guys right here are on sides. These are opposite sides of a parallelogram, so they should be equal. So we could set these two guys equal to each other and solve for b. So I will subtract b from both sides. And then I will add this 1 over, and b turned out to be 4 in that case. I got the other set of opposite sides, and I could set those equal to each other as well. So 2a equals 3a minus 5. I kind of need to move this 3a over so I don't have anything, so that way I have something on this side. So 2a take away 3a is a negative a, and that will be leaving with a negative 5. And then we divide both sides by a negative, and a turned out to be 5 in that case. So those are the opposite sides of a parallelogram. They got to be the same. Here, these are angles in this case. So I know a couple of things. I know that opposite angles are equal, so those should be pretty cut and dry right there. This dude right here is going to be 44 degrees, and I think we'll find it helpful to put that back in the picture. And then to deal with these bad boys, these are consecutive angles,
in a parallelogram, so they need to add together to be 180. So x plus 44 should add up to be 180. Any two consecutive angles in a parallelogram are supplementary. So we take 180 minus the 44, we'll have our x value. So x is 136 degrees, right? So 136. Cool. And then on the next one, they give me the diagonals. The diagonals bisect each other, so these two green dudes right here should be the same, and these two should be the same in that case. So I can take the first one that I had, the y plus 1, and set it equal to 26, because the diagonals bisect each other, and y should equal 25. And then I can do that on my others. X minus 2 should be the same as 19, because those two bros should be the same. So if I add 2 to both sides, x should be 21. Money, money, money. Then I just ask myself, what do they give me? Do they give me sides, angles, or diagonals? They give me the sides, right? So these two opposite sides should be the same. So 10b plus 1 should equal 9b plus 8. I'm going to subtract 9b over. 10b minus 9b is 1b. And then I will subtract the 1 over and get a 7 for that dude. So to find a, same thing, a plus 14 should equal 6a plus 4. I'm going to subtract this a over to this side, so get 5a. Then I will subtract the 4, and then divide by 5. And a turned out to be 2 in that one. So it's a pretty simple game until they give you some crazy stuff right here, right? You know, it's like now we've stepped it up. Like, it is very true that these two guys should be equal to each other because they are the opposite angles, but I don't want to set them equal to each other because one of them has an x with it and the other one has a y with it. So what I'd rather do is deal with these two bad boys because they both have x's, and since they are consecutive angles, they need to add up to be 180. So your 3x plus your x plus 8 adds up to equal 180. And of course, you could have like skipped this move and went straight to combining your like terms. There's really 4x plus 8 equals 180. So if you wanted to go straight to that green line, you can. We'll do that 180 minus 8. And that'll give us a big fat 172. And then we will divide that by 4. And x turns out to be 43. But the crazy thing is, we need to use that to help us find y. So I need to like substitute 43 in for x into either one of those. So 43 times 3, this tells me that this angle right here is 129 degrees, because if x is 43, 3 times that would be 129. And now I can use this because these guys are opposite angles and they should be equal to each other. So if I set the y plus 9 equal to 129, I'm in business. So all I have to do is subtract the 9 over, and I get me a 120 for that. So that was a weird one. They're not degrees either. We're just solving for x and y, so I shouldn't have put that degree sign on there. But that was a weird one. Play with the two guys that have the same letters first, right? So if we look at this, what do we got expressions on? Sides, angles, or diagonals. This is diagonals. What's true about the diagonals? They bisect each other, so that green dude and that pink dude should be the same. And the cool thing is they both have the letter x, so I'm in business. I can set up an equation. And then we will subtract x from both sides and add the 2 over. And then divide by 3, baby. And x turned out to be 4. We're also in business on these guys because they only have y's with them. So we can set them equal to each other because the diagonals bisect each other. And then we could solve that for y. So I will subtract this y over, add that 1 over, and then divide by 2. And y turned out to be 3. So it's a pretty simple game. You're just kind of checking things out. And I definitely wouldn't want to deal with this one and this one because they have different letters in that case. So what I'm going to do is deal with this and this. These are opposite angles in a parallelogram, and according to my hierarchy, they should be the same. So 3y equals 42, and if we divide by 3, y turns out to be 14. But then how do I deal with the x, right? Well, I use this dude, and either one of these, I'd rather use this one because it's already solved for me, it's 42, but these are the consecutive angles, so they need to add together to be 180. So if I add those together, that should be 180, and see these are like terms right here, so you can combine them together. You have a 42 and a negative 6, 42 and a negative 6 is 36. So you have 8x plus 36 equals 180. And then we can solve that bad boy. I will subtract 180 minus 36 and get 144. And then I will divide both sides by 8. And get x to be 18. So another weird one, because we just had to mess around with the variables to make things work out right. And then, of course, we get ourselves a proof. This might be the first time we see this symbol right here. That is the symbol for parallelogram. You can totally use it every time. So they're telling us that we have a parallelogram. That's all they gave us. Awesome. We can use everything we know about parallelograms to get this done. What are we trying to do? Prove these two triangles congruent. Old school, remember, like side, 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 angle, side, and all those crazy bad boys. So trying to get these guys the same. Lots of different things you can do, right? But the parallel lines is something that we could use. Like parallelograms have parallel lines, but isn't it also true that we have like opposite sides the same? So true or false? Shouldn't this side be the same as this side? I think so. So step 2, segment AB is congruent to segment DC, but it is definitely not the definition of a parallelogram. It's because it's one of the properties, so we'll do parallelograms imply, and then whichever property that we had, that opposite sides are congruent to each other. We like to use congruent when we're dealing with congruent symbols, and we use equals when we're dealing with equal symbols, so that is true. And then boom, 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 boom. Can't I get this also? So step 3, I can do segment AD is congruent to segment BC for the same reason. Parallelograms imply that opposite sides are congruent. But I don't have enough information to prove the two triangles congruent, so you can do lots of things. You can do this, angle 1 is congruent to angle 4, because those are like the opposite angles of a parallelogram, so we could do that if we wanted to. Many people just saw that it's like, hey, there's a shared side, so you can do this and get side, side, side. There's lots and lots and lots of things you could do. You could use the parallel lines and say that that angle is the same as that angle if you really wanted to, but we're just going to keep it simple. Why don't we just use the shared side? Boom, boom, boom. Segment DB is congruent to segment DB. And remember that reason is the reflexive property of congruence. So I have the two triangles congruent. Triangle ABD is congruent to triangle CDB. Looks like I was missing a triangle symbol there. Sorry about that. And that is because of side, side, side congruence theorem, baby. So old school proof coming back to us. Hey, let us know if you have any questions. Have a good one.